This is section 5.1, Antiderivatives and Indefinite Integrals. We start with the textbook explanation of an antiderivative. It says that a function, and we're looking at a function defined as big F, is an antiderivative of a function represented by little f if the derivative of big F of x is equal to little f of x. So that's just our preliminary definition, saying that if we have a function who we can take the derivative of to get our target function, then we call it the antiderivative. And that's meant to say we want to work backwards from the derivative. So the function big F of x equal to x to the third over 3 is an antiderivative of x squared. And that's because if we take the derivative of x to the third over 3, we see that when we use the power rule, this becomes 3 times x to the third over 3, and we subtract 1 from the exponent. We see that these 3's cancel, and we're left with x squared, which matches the little f of x function we were trying to match. The book goes further and says, however, f of x is not the only antiderivative of x squared, and we have some examples to look at. And notice that the only difference is they are adding or subtracting some constant. And since the constant has a derivative of 0, that means that we can add any constant to x cubed over 3, and its derivative will make it disappear. And we can say that all of these then are antiderivatives of x squared. And we can write this in a more general sense and call it x cubed over 3 plus c, where c is any real number. And we call this letter c the constant of integration. Integration is the other name given to the process for finding the antiderivative. So we call it the constant of integration. So we have the general sense of it written here. The derivative of x cubed over 3 plus c is equal to x squared. This is what we call the general form, because c could be any number. And as we go through this unit, we'll see that we have the general form and we have the particular form. The particular form will be for a specific constant c, not just any constant. So we go on. Anti-differentiation of a given function does not give a unique function, but the entire family of functions. So a family of functions, we can look at them graphically and see that they're all related by a simple transformation. So x cubed over 3 plus c is a family of cubic graphs. And theorem 1 states that if the derivative of two functions are equal on an open interval ab, then the functions differ by at most a constant. Symbolically, if f and g are differentiable functions on the interval ab, then f prime of x is equal to g prime of x for all x in the interval ab. Then f of x is equal to g of x plus some constant k. So theorem 1 is just to further reinforce the claim that this solution, this general form of the solution, includes all the antiderivatives of x squared. So now we want to talk about this claim of a family of antiderivatives a little bit more. It says, take note that the derivative of x squared over 2 is equal to x. So part A is saying, find all the antiderivatives of x. So all the antiderivatives of x is going to be x squared over 2 plus c. And we said that, even though we saw that this was the simple derivative taken, when we're working backwards, we must include the plus c. That's the constant of integration. So part B says, graph the antiderivative of f of x equal to x that passes through the point 0, 0, through the point 0, 1, and through the point 0, 2. So what this means is we have a function f of x equal to x squared over 2 plus c, and we want to evaluate it at the point 0, 0. And what this means is that f of 0 is equal to 0. And now we can write that in our equation. 0 equals 0 squared over 2 plus c. And this gives us c equal to 0. And now we have a particular f of x that is equal to x squared over 2. And you can work this out for 0, 1 and for 0, 2. And you'll find that f of 0 equal to 1 will mean that c equals 1, and that'll give us an f of x equal to x squared over 2 plus 1. And that f of 0 equal to 2 will imply that c is equal to 2 and give us an f of x equal to x squared over 2 plus 2. Part C asks, how are the graphs of the three antiderivatives in Part B related? So let's complete the graphing step of Part B. If I am graphing x squared over 2, when I plug in 0, I get 0. If I plug in 2, so f of 2 would give me 2 squared over 2, which is 2. And if I plugged in 4, that would be 4 squared, which is 16, divided by 2 is 8. So that's what the graph would look like on the right side. It's a parabola, so it would mirror it on the left side. And if you look at these, they're the same function, but they're just translating up 1 unit. So every point would just go up 1 unit. And then plus 2 would start with the vertex at 2. And now we can answer part C. We could say, well, the graphs are just vertical translations of each other. They have the same base graph, the x squared over 2. That's our parent graph, we can say. And we're just shifting it up 1 unit for x squared over 2 plus 1, or we're shifting it up 2 units for x squared over 2 plus 2. So they're just vertical translations. So we continue now. They give us some formulas that we can use here. It says that when we are looking for the antiderivative of x raised to a power, then we can add 1 to that power and divide by that new exponent. This is the power rule in reverse. So remember, dx of x to the n, when we were finding the derivative, would say multiply by the exponent and then subtract 1 from the exponent. Well, if we were to reverse that, the reverse says add 1 to the exponent, then divide by that new exponent. And that's what this is. This is the power rule for derivatives in reverse order. This is our e to the x antiderivative in reverse order. If the derivative of e to the x is itself, then the antiderivative of e to the x is itself plus the constant of integration. And here is the reverse order for our log rule. If the derivative of natural log is equal to 1 over x, then the antiderivative of 1 over x is equal to natural log. They just have one caveat. Make sure you use the absolute value with the antiderivative. This is to avoid any domain issues that would arise because natural log is defined for x greater than 0. And to continue with our rules and properties, we see that if there is a constant multiple of a function, just to give you a concrete example, if I had 3x squared dx, I can take that constant and move it out front and focus on the x squared dx. We've done this with constants throughout the entire course, whether we were talking about limits or derivatives. and now we're talking about with antiderivatives. So constants can be moved outside of the operator, and then we can look at the simpler function. And now this is the power rule in reverse. So we would say x to the third divided by 3, because we're adding 1 to the exponent, then dividing by that new exponent. But don't forget this 3 over here we need to multiply by. And then we have our plus c. This would cancel. So the antiderivative of 3x squared dx would be x cubed plus c. And part 5 is saying if we have multiple terms, we can break them down into individual antiderivatives. We've done this in the past with limits and with derivatives. Now we're seeing this with antiderivatives. If I had e to the x plus 3x dx, I can separate that to e to the x dx plus 3x dx. And then you would use the e to the x rule for the first one, and you would use the power rule for the second one. And this would give us e to the x plus 3x squared over 2 plus c, using those individual rules. All right, so let's spend more time practicing. Here we have a constant, 5. And you should say, well, when do I get a derivative that gives me a constant? When does a derivative result in a constant? And if you think of some examples, the derivative of 2x would be 2. The derivative of negative 7x would be negative 7. We see that whenever we have a constant, that means there was a linear function and that the derivative is just the slope of the linear function. So we can reverse this and say there used to be an x next to this 5, and now I'm going to add a plus c, and that would be your answer. So whenever you have a constant, simply put an x next to it and follow it with a plus c. Part B, 9e to the x. We can take the 9 out in front of the operator and say, well, what is the antiderivative of e to the x? You'll get e to the x plus c is its antiderivative. And if you distribute the 9 through here, you get 9e to the x plus c. And that's your answer. Now, students will say, well, how come it's not 9e to the x plus 9c? Nine times an unknown constant is simply an unknown constant. These are saying the same thing. This is just the simplest form of an unknown constant. So is 9e to the x plus 9c wrong? No, it's not wrong, but it's not the simplest form, and we want the simplest form of the answer. So part C, we're going to take the constant out again. We're left with t to the 7th dt. We see that this is the power rule in reverse. So add 1 to the exponent, and that gives us t to the 8th. Now divide by the new exponent. That gives us t to the 8th over 8. Now bring that constant back, that 5, so it's 5/8 t to the 8th power. And don't forget the constant of integration. You can always check your answer by saying, well, what if I take the derivative of this? D dt of 5/8 t to the 8th plus c. And we say, well, using the power rule, we multiply 8 down here, and we get 8 times 5 over 8 t to the 8 minus 1 power plus 0, because the derivative of any constant is 0. And we say, now that we've written it this way, we see that the 8's cancel out, and the 8 minus 1 becomes a 7, and we're left with 5t to the 7th power, which is exactly what we started with. So anytime you get your answer, you can say, well, let me take the derivative of my answer. What's the derivative of 9e to the x plus c? Well, derivative of a constant is 0, that disappears, and 9e to the x is its own derivative, so that answer works out. What's the derivative of 5x plus c? C goes to 0, derivative of 5x is 5, that works out. Anytime you get your antiderivative, simply take the derivative and see that it matches the starting problem, and that's how you can check your work. If you look at problem D, we have multiple terms. We can break this up into multiple antiderivatives. I can break this up into 4 times the antiderivative of x cubed plus 2 times the antiderivative of x minus the antiderivative of 1, and each of these have a dx after them. So we're left with 4, and we say using the power rule, I'm going to add 1, which gives me 4, and divide by 4. So this is x to the 4th over 4, plus 2. This x is understood to have a 1 as an exponent, so if I add 1 to it, that becomes x squared. Then I have to divide by that new exponent. And whenever we have just a constant, we understand that gets an x next to it. And now that I've taken the antiderivative of all 3 of these, don't forget our constant of integration. And now we can simplify. We see that the 4's cancel and the 2's cancel. So our answer for problem D is x to the 4th plus x squared minus x plus c. And for part E, we can break this up into 2 separate antiderivatives, 2 times e to the x dx, plus I'm going to take this 3 and put it out in front, 3 times the antiderivative of 1 over x dx. We see that e to the x is its own antiderivative, so we have 2e to the x plus 3, the antiderivative of 1 over x. That's natural log of the absolute value of x. That was one of our rules for this section. And now plus c for the constant of integration. And that would be your answer to problem E. So pause the video here, try these out on your own, see how you do, and then unpause to see the results. So for part A, because it's a fraction, I can rewrite this using negative exponents. Now I'm going to add 1 to my exponent. So add 1 to negative 3 and you get negative 2. We're going to divide by that negative 2. So part A, we get 4 divided by negative 2 is negative 2x to the negative 2 power plus c. And this is correct, but I can get rid of this negative exponent by writing negative 2 over x squared plus c. And this is the preferred form for this problem and for the answer to this problem. Okay, so part B, let's rewrite this using exponents as a way to express it. The antiderivative, I'm going to move the 5 out front, and this is u to the 2/3 power, du. Now we would like to add 1 to the exponent. So 1 is 3 over 3, we get 5/3. So we're going to divide by 5/3. But when you divide by a fraction, it's the same as multiplying by its reciprocal. And don't forget to bring this 5 down from outside. And don't forget to plus c. So now these 5's cancel, and we're left with 3 times u to the 5/3 plus c, or you can say 3 times the cubed root of u to the 5th plus c. Or you can simplify this radical and say 3 times u to the cubed root of u squared plus c. So all 3 of these answers are correct. They're just different forms of expressing them. And it's good to practice this so that if you were to encounter a multiple choice question, you can identify one of these 3 forms as the right answer. Now at problem C, we're going to rewrite this as x cubed over x squared minus 3 over x squared. And what we've done here is said this is a fraction that was joined, 2 separate fractions that became 1. Well, let's split it back to two separate fractions. And now we can simplify the first fraction. X cubed over x squared is x. And minus 3 over x squared can be written as minus 3x to the negative 2. And now we can use the power rule for each. So we get x squared over 2 minus, when you add 1 to negative 2, you get negative 1. And when you divide by negative 1, that makes this a plus 3x to the negative 1 plus c. So this is correct. Or I can take that negative 1 exponent and turn it into a fraction. X squared over 2 plus 3 over x plus c. Both of these answers are correct. So we're back to talking about the particular solution to antiderivatives. And the particular solution means that we are solving for a specific c. And to find a particular solution, you must be given a point on the curve. So the problem says find the equation of a curve that passes through the point 2,5 if the slope of the curve is given by dy dx equals 2 over x for any point x. So remember that derivative finds slope. That's what we've been doing with derivatives this year. So equals slope at a point on the curve. We would like to find the actual curve. So to do this, we want the antiderivative. So we're going to use this symbol, the antiderivative symbol of 2x. That's what's calculating the slope for any point x dx. And when we do this, we see that we get 2x squared over 2 plus c, which simplifies to f of x equals x squared plus c. And we're saying that f of 2 is equal to 5. So 5 is equal to 2 squared plus c. 5 is equal to 4 plus c. 1 is equal to c. And if we plug that back into here, we now have the particular solution. This is the general solution because c is unknown. But now the particular solution is f of x equals x squared plus 1. So here we have a word problem. If the marginal cost of producing x units of a commodity is given by c prime of x equal to this function, and the fixed cost is $2,000, find the cost function of c of x and the cost of producing 20 units. Well, fixed cost is the cost before you produce anything. So that means after producing 0 items, you have a cost of 2,000. That's our point that's going to get our particular solution. To find our cost function, c of x, it's going to be the antiderivative of our marginal cost function, c prime of x. So the cost function is the antiderivative of 0.3 x squared plus 2x dx. And now we want to add 1 to the exponent. This second one is understood to be a 1, so we'll add 1 to that exponent. We divide each term by their new exponents. And we see that c of x is equal to 0.1 x to the third plus x squared plus c. And now we can say that c of 0 is equal to 2,000. And that means that 2,000 is equal to 0.1 times 0 cubed plus 0 squared plus c. Since these terms zero out, we see that 2,000 is the value of c. And now our particular solution is 0.1 x cubed plus x squared plus 2,000. And we can find c of 20 now. So we will type 0.1 times 20 to the third power plus 20 squared plus 2,000, and we get $3,200. So here we have an advertising problem. It states a satellite radio station launched an aggressive advertising campaign 16 days ago in order to increase the number of daily listeners. The station currently has 27,000 daily listeners. The word currently means right now, so that means at time zero, we have 27,000 listeners for the station. Management expects the number of daily listeners, represented by the function s of t, to grow at a rate of s prime of t equal to 60 t to the half power listeners per day, where t is the number of days since the campaign began. How much longer should the campaign last if the station wants the number of daily listeners to grow to 41,000? Well, we see that s of t is equal to the antiderivative of s prime of t, which is 60t to the half power dt. We can evaluate this by using the power rule, and 1/2 plus 1 gives us 3/2, so we're going to divide by 3/2 with a plus c. And dividing by a fraction, we understand, is the same as multiplying by its reciprocal. So we have an s of t function equal to 40 t to the 3/2 plus c. Now we'd like to solve for c using our initial condition, 0, 27,000. And that means that 27,000 is equal to 40 times 0 to the 3/2 plus c, which means that 27,000 is our c value. So now we have a particular function equal to 40 times t to the 3/2 power plus 27,000. And we want to solve for when the number of listeners will be 41,000. So we subtract 27,000 from both sides. That gives us 14,000 equals 40 t to the 3/2. Now we divide both sides by 40, and we get 350 is equal to t to the 3/2 power. We would like to get t to the power of 1, so t to the 3/2 power raised to the 2/3 power, a power to a power multiplies and will give me t to the first. And anything I do to one side of an equation, I must do the same thing to the other side. So we will have 350 raised to the 2/3 power equals t. 350 raised to the 2 divided by 3 power gives us 49.66 days, so approximately 50 more days. So this is the end of the lecture. Go back, rewatch the video, write down questions, and bring them to class.